Good morning, everyone. I'm Nitin Agrawal from NEC Labs. And today I'll be talking about our work on revisiting storage for smartphones. This is joint work with Hyojun Kim and Cristian Ungureanu. So smartphones, tablets, and other mobile devices are now becoming a way of life. The iPhones and the Androids of the world have fueled the mobile fire, and we are living in what some call a post-PC era. So not only are the mobile users, growing in number, and the fact is more smartphones are now being sold than PCs put together. This number is a bit dated. Mobile users are also potentially more active, as suggested by their Facebook usage. Mobile hardware is also constantly evolving, right? So you want to pack everything that you want to do in the smartphone. So Samsung Galaxy Note that just came out combines a phone with a tablet, providing a pen for input, kind of opening up all sorts of new user interaction with the phone. Phones are also being equipped with a lot of attractive hardware add-ons. So NEC's Media's phone packs in a number of hardware goodies in a thin casing. And there are lots of other sensors and hardware peripherals that are being added to these devices that open up new ways of using them. Manufacturers are in fact making it more and more attractive to altogether replace PCs with mobile devices. And so Motorola Atrix has a dock that converts your phone sitting right there into a laptop. Pretty cool. But it's not just the hardware, right? What we do with it is important too. And credit goes to the mobile app developers and users who have done a spectacular job of using the school hardware. And we all run some simple apps, things like web browsing and maps and email. And I know some of you might be checking your email right as I speak on your mobile phones. And sometimes we check Facebook or other social networking sites. Every now and then we share music and files. And of course, there are games like Angry Birds that we are all known to be hooked onto. But we're also beginning to use our devices for more demanding apps, things such as full phone sync and backup, indexing, augmented reality, HD video, virus scan, you name it. These apps are as much a driving force in the mobile ecosystem as the hardware. And smartphones are being used for a whole lot more than just calling and texting. While we spend quite a bit of our lives using these apps on a day-to-day basis, unfortunately, a big chunk of that is spent waiting for a website to load, or a music file to download, or a news feed to refresh. That's not good. That's clearly undesirable, right? More time waiting is annoying for the user. It's especially true for mobile users who tend to be more interactive. In many cases, more time means more battery being spent for the device. And from the developer's perspective, it's easy to lose customers if they don't have a great experience. But when you talk about mobile performance, aren't network and CPU the real problem? Why are we talking about storage? These are valid questions, and I hope by the end of the talk, you'll have a better idea of why that is. So let us review some aspects of the mobile environment that all of us seem to know. So network performance clearly impacts user experience and the performance of applications. This we understand quite well. 3G is often considered the bottleneck for applications like browsing. And service providers understand that and are aggressively working on improving cellular bandwidth, improving 3G, 4G. And so there's tons of work going on in academia as well, on how to better use our wireless resources. CPU is also clearly important. Graphics performance is crucial for a lot of the applications that we use. There's plenty of gaming, video, flash player apps that are hungry for compute. And so that's well understood as well. And that trends like quad-core CPUs and GPUs that are beginning to appear on these devices. While these are well understood, one aspect that has, in our opinion, not been well understood is the contribution of storage to the mobile experience. So does storage performance impact the mobile experience? So far, the reference to storage almost always has been in the context of capacity. Let's look at how storage performance compares with network performance to see if that gives us a clue of why this is a relevant question. So the figure here shows the progression for both local in blue and wide area wireless networks in green over the past 3 decades. The y-axis is logarithmic, and the graph plots peak speeds as defined by the standards, not measured. We did go ahead and measure a few of them, the relevant points in the lab, just for comparison. So the blue and green circles show the measured speed for 3G and 802.11 ANG, while the red dot shows peak measured speed for a good quality flash card used in mobile devices. So a few things to notice here. Network performance has clearly steadily increased over time for both local and wide area. However, from a storage perspective, things seem to be fine since flash storage performance exceeds typical network connections that we use. So this is kind of the first thing that we notice, right? Since most applications tend to be interactive, as long as the performance of the network subsystem exceeds that of storage, it is difficult for the storage to be the bottleneck. These conclusions are unfortunately not true and form the basis for the rest of the talk and our work. So this is outline for the rest of my talk, and I will start the discussion of why storage is in fact a relevant contributor for mobile application performance. So one of the fundamental properties for the majority of for storage devices is the disparity between random and sequential performance. And for disk, we all know the performance for random I/O is significantly worse than sequential. That's also true for flash-based storage in some contexts. However, mobile flash storage is typically classified into speed classes based on their sequential throughput. So the table here, what we did is we went ahead and bought a few cards, in fact 2 each from the different speed classes. So we have 8 cards here, and we measured their performance. So I'm listing the cards, their speed classes, and just the cost to just give you an idea. So while sequential performance is not great, it's in megabytes per second. The rightmost label is getting cut off. Sorry about that. It's not great. It still looks okay. However, random write performance is in orders of magnitude worse. So the red, the text in red shows the random write performance, and we see that clearly it is a far cry from what we're getting for sequential performance. Now, this would all be still a non-issue if I/O to the mobile storage were to be mostly sequential. But through our analysis, we find that for several popular applications, a substantial fraction of I/O is indeed random writes, which is a bad scenario for flash storage. And this includes interactive applications such as web browsing. This, in a sense, is one of the root causes of the storage problems. So if you take a second look at our previous graph and plot just a set of random performances measured from these various cards, we find that the random performance is in fact much, much worse. Furthermore, one of the underlying trends is the shift in performance bottlenecks. So storage performance has clearly not kept pace with the improvements in the network. There are faster networking technologies such as 82.11n and 88AD that offer potential for significantly faster network connectivity to mobile devices in the future. And this could potentially further park the bottlenecks into the storage domain. So this combination of the flash performance and these trends point to a problem here. So now we take a deeper look into how exactly the storage is being exercised on these devices to be able to understand and address this problem. So the focus of our work is to understand the contribution of storage to the mobile user experience. And as we started this work, the subsequent question we asked ourselves was whether this affects the common and popular apps on our smartphones and not just benchmarks. So while we did experiment with some Linux workloads, we ultimately constrained ourselves to the apps that everyone uses. And we chose Android for the obvious reason that it allows systems-level development and access. Through our study, we made several interesting observations through this measurement and analysis. We found that, of course, storage adversely affects performance of even interactive applications, including ones not thought of as storage I/O intensive. We found that the speed classes are although meant to indicate sequential performance, they don't give a good estimate of how the app would behave. We also found some initial results in non-performance related issues, such as finding higher CPU consumption for the same activity with slower storage. And this could point to potential problems with the OS or how the apps are written. It's a fertile area for future research. And finally, we proposed some solutions to improve the storage stack to help give a better mobile experience. And in this talk, I'm going to focus on the performance issues. So before talking about the results, I'm going to give you a brief background on Android storage schema and our experimental setup. So let me tell you a little bit about Android storage schema. So the top picture that you're seeing shows the storage partitions on an Android phone. We show it for the HTC Desire Google Nexus 1. But the setup is fairly typical across Android devices. So as you notice, there are a bunch of partitions listed on the left and a brief description of what the partitions are. Let me just walk you through real quick. So the first set of partitions is for device hardware configuration, and it contains the boot partition, which contains the bootloader and the kernel. The second set of partitions are what are more relevant for our work, which contain the system partition, which contains the actual OS and all the pre-installed apps, and the data partition, which stores all the user data, and it stores all the application data as well. In the case of Android, the applications are provided with a well-defined interface to create, query, and manage their own databases. So one or more SQL-like databases are stored per application on the /data partition. And this is the partition that gets deleted on a factory reset. The third set of partitions is the external partitions that store larger files like music, videos, and documents through a file system. Let me give you a brief summary of our experimental setup. The paper has, of course, more details on how we set up the phones for this kind of analysis. So we rooted and set up a Google Nexus 1 phone for development. We also set up a dedicated wireless access point because we were conducting measurements with Wi-Fi. And we installed the Android open source project with a customized kernel that gave us some resource user information. So this was a kind of a generic setup that many of you might have already done for other things or just for fun. In addition to the generic setup, our experiments required some capabilities from the system that were not possible with the stock phone and Android setup. These are a little bit more interesting for us. In particular, we wanted the ability to compare application performance on different storage devices. Now, several applications, quite a few of them, heavily use the internal, non-removable storage. So, we could not really do much with that. So for experimentation, in order to observe and measure all I/O activity, we modified Android's init process to mount all internal partitions to the external SD card. And we performed the measurement study over the internal flash and the 8 external SD cards that I had briefly summarized in the table. We chose the SD cards, 2 each from the different speed classes, just to cover the spectrum. And given the trends towards faster networks and the potential to shift bottlenecks, we were also interested to observe the effects of these new networking technologies. But faster networks, wireless networks, are not available on the phones of today. So we had to emulate them. So we did that by using something called reverse tethering, which emulates faster networks by allowing the smartphone to access the host computer's internet connection. In our case, we used it through the wired mini USB cable. And we also did some instrumentation to measure CPU storage, memory, and network utilization. So I will note that although this setup is not typical of how end users use their phone, it enables us to run what-if scenarios with different storage devices and network characteristics. The slide here shows the set of applications and the benchmarks that we use to perform our measurement. The point I just want to make is that we tried hard to choose applications that are very popular and that all of us use in our day-to-day lives. And for many of the applications, the benchmarks, we measured the total amount of data transfer and normalized. We ran the experiment multiple times in control settings. So we did all that to ensure that the results hold steady. I'm going to focus on WebBench for this talk. That's the web browser application. But the paper has more details on other applications in different scenarios. So I'm now moving on to the experimental component of the talk. I'm going to present some results. In this talk, I'm just going to pick a subset and focus on the runtime of applications. The paper has a lot of other results on I/O activity, CPU, and application launch behavior. And what I'm going to do is first present the observations and then kind of dig deeper into why we are seeing the phenomena that we are seeing. So the graph here shows the runtime for the WebBench, which is the web browser application, for the 8 SD cards and the internal flash. So the x-axis is just a label of the different storage devices. The y-axis is the time in seconds. And note that there are 2 bars here. So the dark blue bar is the time taken on the Wi-Fi network, and the light blue is on the emulated USB network. And just to give you a sense of drawing the baseline, the Wi-Fi is about 8 to 12x, about 10x on average, faster than the USB. So the right graph shows the time taken for iPerf to download a 100 megabyte file. So just to give you a sense of how fast the wireless network is. So we note that the card in the middle, the Kingston card, performs quite poorly and skews our results. And we thought it's an experimental error, so we repeated the experiment several times. When that didn't work, we just bought new cards, thinking that we had some problem with our specific card, and we bought them across speed classes, but the results pretty much stood steady. So what we're doing is, in order to not rely on Kingston alone to make the points that we're trying to make, we're going to discount Kingston and still try to see if we can convince ourselves that this is really a problem. So the graph now shows the results without Kingston in the loop. And even now, the performance variation is pretty reasonable. It's about 200% between the best and the worst case. So we find that storage significantly affects application performance and consequently the user experience. With a faster network, the USB in reverse tethering, the variance was a little bit higher, about 220%. That's without Kingston. However, I think the big takeaway or the surprise for us was that with a 10x increase in network speed, there is hardly any difference in runtime. Now, this was the thing which kind of made us believe that in this case, at least, the network is clearly not the limiting factor. That we were hoping to see the performance improve quite a bit with this faster network, but that didn't happen. So this was a surprising result and forced us to rethink some of the assumptions we were making about mobile storage usage. And the problem is not with WebBench alone, but we found similar trends for a variety of popular applications like Facebook, Google Maps, Android email, application install for a bunch of applications, a SQLite benchmark, a newsreader. Found a similar trend across several popular applications. And again, in all these graphs, I'm taking out Kingston, because with Kingston, the graphs are just even more chaotic. So we find the storage device performance is important in many, if not all cases. Better cards typically lead to better and faster applications. But the question that kind of kept us going was that apart from the benefits provided by selecting a good flash card, so we could all go and pick a nice card, and maybe that will help us improve the performance by some extent. But are there additional opportunities for improvements in storage? Are there some fundamental ways in which we are using the storage in a bad way that we could improve? So let us look at some of the underlying causes which probably help us understand this challenge. So the table here, the graph here shows the relative performance. It shows the breakdown of the sequential versus a random I/O, again for the browser application. The y-axis is the cumulative I/O in megabytes on a log scale, and the x-axis is the time in seconds. So the graph shows the breakdown of I/O activity in terms of sequential and random writes, and sequential and random reads. So we find that there are few reads for this experiment, mostly at the start, and there are significantly more writes. In fact, there are about 2x more sequential writes than random writes. However, we also found, if you remember the table for SD card performance, random is much worse than sequential. And so the table here lists the sequential to random performance ratio, and we find that even in the best case, it's 4. In most cases, it's hundreds, and in the worst cases, it's like 1,000, factor of 1,000 or more. So clearly, random write performance dominates in this case. And apps write enough random data. They don't write all data randomly, but they write enough random data to actually make random write performance a contributor and cause a severe performance drop. And the paper has a table on I/O activity for the other applications that I showed you the runtime graphs for. So random writes are part of the problem, but why so many random writes? What causes them? So we were really interested to know what was going on, because that probably gives a clue of how to fix the problems. So we dug deeper and tried to understand exactly what makes web browsing so slow on Android. We found that the key lies in understanding how apps use the SQLite and the file system interface that is given to them. So the picture here shows just a schematic of a WebBench storage schema. And kind of two things to note here. There is a WebView cache, which is where the browser stores its cache objects, or the files. And these files are written to the file system in a write-behind mode. However, there is other set of files, the databases files, which includes a cache map or a SQLite database that stores an index for the cache objects. And these files are written to SQLite in synchronous mode. And this is fairly typical across other applications. So the applications use this interface to store some data in the file system, such as cache files for browser, and some in the SQLite database, such as the index for the browser. And all data that is written through SQLite is written synchronously which makes it slow. And apps often use a SQLite interface oblivious to performance effects. It's there for convenience, it's there for modularity, and that's nice. But there are performance implications which somehow get lost in this nice abstraction. So before implementing solutions, we wanted to understand if there was any room for improvement. We wanted to understand what is the potential. For example, if all data could be kept in RAM, what is the kind of upper bound that we could expect? So to answer these hypothetical questions, we performed a what-if analysis for the solutions. So we evaluated 4 hypothetical scenarios for the case of the browser experiment. We said, let's assume that we can put the entire cache in RAM. Or we could put the database, the SQLite files, in RAM. Or we could put everything in RAM. Or we could put everything on the SD card, but turn off the synchronicity of SQLite. And what we found was interesting. So again, the x-axis is just the techniques that we tried. And the y-axis is time taken to run the WebBench experiment. The black bar is the baseline without any of our what-if improvements. And we found that placing the cache on RAM disk alone does not improve performance much, which is kind of expected. However, placing the database on RAM disk alone improves performance significantly. Placing both the cache and the database in RAM did not give much additional benefits while taking up a whole lot more RAM. And finally, even putting both in cache and database on SD card without the sync operation actually recoups most of the performance. So this kind of, in retrospect, seems very obvious and straightforward, but going in, we had no idea that we were actually going to find these observations, and we could put it all together and try to understand what's going on. So some takeaways, just to summarize the takeaways from our measurement study and this what-if analysis, we found that storage stack definitely affects the mobile application performance, and the performance actually in turn depends on the ratio of random to sequential I/O performance. We found that the key bottleneck in some sense is the wimpy storage on these mobile devices. And the storage found in mobile phones, the performance can be much worse than what storage we typically use on laptops and desktops. But the kinds of applications we run on these phones and tablets are becoming more and more desktop-like. So the hardware is not designed with imagining those kind of activities. And perhaps more significantly, the Android interface exacerbates this poor storage, poor device performance through the synchronous SQLite interface. And apps use the interface for functionality for good reason, but not always needing reliability. And the SQLite write traffic is quite random, which provides this slowdown. So as I said, just give an example, the applications use this interface oblivious to performance. For example, the browser writes this cache map to SQLite, which slows down the cache writes altogether. So now I'm going to talk a little bit about the solution space that we tried to explore. I just want to mention that we implemented and evaluated a few pilot solutions. So you can think of them as kind of quick and dirty prototypes to calibrate the solution space and provide envelopes of improvement. And we believe that the solution space is in fact fertile ground for more innovation and try to build these phones with better storage underneath. So the first thing that we just kind of thought as a thought experiment, that there is already some I/O parallelism that is available to us. So most phones, if not all, have an SD card and an internal flash. So how about we just stripe data over these devices? So we build a simple software RAID driver that stripes I/O to these two devices. And we found an as-expected speedup about 1.5 to 2x, just because we're just doing striping. In some cases, however, we were surprised to find a superlinear speedup. And we traced it back to some idiosyncrasies of the flash, of how the FTL worked with kind of the degree of randomness. And there's details of that in the paper, if you're curious to know why that was happening. We also saw that since phones started with this log-structured file systems in the beginning and then kind of gradually moved on to ext-like file systems, how about we just try if you use a log-structured file system? So we used nilfs2, which is a block-based file system, log-structured file system, to store the SQLite database. And we found some moderate benefits, not too much, and we kind of attributed to the inefficiencies of nilfs2, which is not super optimized for this kind of usage, and just the overheads of log-structured file systems in general. But I guess there is some room for further improvement if we really try to optimize, squeeze out more from them. Another set of solution space potential is what if we could just modify the applications, right? And that's always a tricky thing to propose because there are trade-offs in ease of development and benefits of performance. But if we were to turn off sync for files that we thought do not need synchronous operations, for example, in the case of WebBash, the web browser, we turn off sync for just the database index for the cache. We saw some improvements, and of course, in this case, the benefits depend on the app semantics and the structure of the application. And finally, if you place a small amount of PCM, a faster write buffer alongside to store just the performance-sensitive I/O, for example, the SQLite DB, we found that it goes a long way. So I'm going to just touch on two experimental results we show for the browser and Facebook application. The black bar on the left is the baseline. The rightmost bar shows the time taken as an upper bound if all data was in RAM. With the rate solution, we found, again, like a 1 to 2x, typically 1.5x improvement. For the log switch file systems, we found about 20% improvement. In some cases, the improvements actually were more for some of the poor performing flash cards. The selective sync solution gave us, again, like dependent on the application, some benefit. For example, for Facebook, it was about 100%. And finally, the PCM solution kind of took us a little bit more closer to the all in RAM bound. So to conclude our talk, in our work, we found that contrary to conventional wisdom, storage does affect mobile application performance, and effects are pronounced for a variety of interactive applications. We developed some pilot solutions that hint at these performance improvements. We found that small degree of application awareness leads to efficient solutions. And we believe that although more work is required to make these solutions robust and deployable in the future, we now have some understanding of how to proceed. And finally, we believe the storage system and mobile devices need a fresh look. And we have taken the first steps. There's plenty of exciting research ahead, we believe. And I hinted at the CPU problem earlier on. If you're a student interested in this space, come talk to us. We have lots of ideas. We don't have the time to work on all of them. So, and thank you very much.
So Jeff Tenning, Harvey Mudd College. And this is another one of my weird for the room questions, I guess. So this reminds me, of course, of the Wisconsin paper that was presented at SOSP, where they found that applications running on Apples were doing absurd numbers of unnecessary syncs. And I'm thinking that over the years we have had to deal with the baroqueness of disk drives. And we have to because disk drives are baroque, but are we now getting stuck with dealing with what really is just plain stupid applications? Is that the new direction for file systems research?
Well, so I guess it's a philosophical question, and the answer could be very long, so I'll try to keep it short. So I guess the common theme in that paper and ours, just to give a more concrete answer, is that we are seeing a trend in which applications and operating systems are written in a kind of a modular way. And part of the motivation is just to help application developers. The modularity is good in many cases. It is not good in some cases. And performance is just an unfortunate kind of victim of that modularity. Now, we could force ourselves to write a more structured, a better designed application stack that provides greater flexibility, but there are trade-offs. And we believe that there is some room for making it a little bit more flexible so that at least you can specify what you really need to be, for example, reliable and persistent, and what you don't. And I think that's a step in trying to cover the spectrum of the kinds of things we are seeing for Mac desktops and for mobile devices. Thank you.
Hi, Eno at Microsoft Research. So I believe that storage is going to be a bottleneck. I just don't know. Does it really matter end to end? Like as people are using these things? You have the benchmarks there, but I mean, I kind of read the web pages kind of slow, and I have to admit I'm pretty satisfied with the performance overall, and I'm looking more at things like UI and.
So are you talking about whether these applications are used or not?
More like have you asked users like what is their perceived. What is their feeling? Did this perceive like the end-to-end experience? So
the thing is that we were the users in these cases, right? I mean, in the sense that these are experiments all that are interactive. So it's not like a tar or anything. So WebBench, for example, we actually open the website and wait for it to load. Facebook, we click some buttons, wait for the news feed to refresh. In Maps, we press like from to, click to find the direction. So these are, I mean, almost all of them, if not all, are interactive applications. And in many cases, we wrote like monkey runner scripts to automate the GUI interaction, but they're still interactive. And yes, we found that this is all measured at the application at the user level. So the time you see in the variance in the runtime is all measured at the user level. So I believe that why would anyone want to see a 20-second wait if they can only get away with 3 seconds, particularly if the network is not a problem.
Okay, thanks.
Let's thank the speaker one more time.